Atkinson cycle. Okay, so first example. Now, at the beginning of the adiabatic compression of an Atkinson cycle, the pressure, volume, temperature are 101 kPa or 1.01 bar, 14 liters. Remember how to convert liters to meter cube. That is basically divided by 1000. And then the temperature is 15 plus 273. Now, at the end of the adiabatic compression, the volume is 2.8 liters divided by 1000. The maximum pressure of the cycle is 1.85 megapascal. That means 18.5 bar. Determine the thermal efficiency, the heat supply, the heat rejected, that is cooling, the network output or the network, the work ratio, the mean effective pressure, and the Carnot efficiency. They have given us the gamma as 1.4 and the R, that is the specific gas constant, 0.29. You can actually based on gamma and R, you can find out the CP and the CV value. Okay, you can find the CP and the CV value from the very previous slides that I have given you. Because I cannot be putting everything on one slide itself because it will add in contents. Okay. So now this is Atkinson cycle. It consists of two reversible isentropic processes. Okay, one reversible constant volume process and one reversible constant volume process. Okay, so these are the two isentropic process, 1, 2, and 3, 4. Now 2 to 3 here is constant volume, 4 to 1 is your constant pressure. So draw this on your TS. It should look like that. 1, 2, and 3, 4 is isentropic. Okay, 2, 3 is constant volume. So this must be steeper actually. This must be steeper. Okay, must be steeper. And then this is constant pressure, 4 to 1, less steep. Okay, so basically this is your PV and TS diagram. So you can do some amendment on your own, drawing your 2, 3 much steeper up. Going up steeper. Okay, so these are the 4 processes. Remember, heat supply should be here, as you can see from the TS. By now you should know how to look for heat supply and heat rejected based on your TS diagram. 1 to 2 isentropic, no heat flow. 3 to 4 no heat flow, isentropic. Only heat flow occurs at 2, 3 and 4, 1. 2, 3 is constant volume and 4, 1 is constant pressure. So this is the table that I have prepared. So the pressure, volume, and temperatures are given. Okay, so this you can take 14 divided by 1000. Okay, so you got the pressure, volume, and temperature. So you can find out the mass based on this. So based on ideal gas law. Okay, ideal gas law on state point 1, that is your mass. Okay, so you have to find out your mass, which is 0.01693 kg. Then, okay, now we know the volume at point 2 as well, because they say at the end of the adiabatic compression. This is the adiabatic compression. So at the end, that means your point 2 is here. Your point 2 is here. So at the end, that means V2. So given 2.8 liters, so that is equivalent to 0.0028. So based on 1 and 2, which is isentropic compression, so that is why you can use the pressure-volume relationship. Now the gamma actually, okay, if you can work it out, is much better. Okay, otherwise you can consider this as 1.4. So state point 2. Now, when you refer to state point 2, we got this pressure and this volume. So that is why when you refer to ideal gas law again, you would be able to find out your T2, which is 548. Okay. Then now, when you look at 2 and 3, the volume is the same. So that is why you can put these two volumes the same. And then when you refers to 4 to 1, the pressure is the same. So you can fill up your pressure 1 and 4 as well. 2 and 3, the volume. Okay. So we know everything on row 2 and row 1. And then we know the maximum temperature, which is already given in the question. And then we know the volume because we have found V2, which is equals to V3 here. Then ideal gas law again to find out the temperature T3. Okay, so that should be your T3. So row 3 is completed with the pressure we got. Okay, then 3 to 4 here, you can see this is isentropic. So based on isentropic, again, you can also refer to the isentropic relationship between the pressure, volume, or pressure, temperature. Okay, if you take pressure, temperature, it must be power of gamma minus 1 over gamma. If you take pressure to volume, so it must be power of gamma. Okay, P1 equals to P4. So in the diagram, you can see. So based on isentropic process, so you can take the relationship between pressure, volume. P4 we also got, okay, gamma 1.4, so you will be able to find out V4, your V4. Then can find out the last temperature T4 by applying ideal gas law. Remember there's a mass here, yeah? And then the heat supply, heat ejected, all in kilojoules. Then you multiply by mass. Remember, when you multiply by mass. Okay, so it should be in kilojoules. So CVT. Why CVT? Look at heat supply, 2 to 3. 2 to 3 here is heat supply, constant volume. So that's why it's CVT. Okay, the maximum temperature of the process minus the minimum temperature of the process. Maximum is T3, minimum is T2. Then multiply by your mass. Okay, so you get your heat supply. Then the next thing is your heat rejected from 4 to 1. Okay, so there's a mistake here. This should be CP because 4 to 1 is CP. Yeah, so you have to use your formula of CP. So this is CP, yeah, not CV 0.718. So a mistake here again. So you will be able to find out your heat rejected. So you can work out your work. You can work it out on your own by changing this CP value to check whether this value here is correct or not. Okay, because sometimes it's due to my typing error. So once you got heat supply and heat rejected, you can find out your network. Because is heat supply minus heat rejected over heat supply. So that is your thermal efficiency. Okay, so that's your network out. So gross work expansion. So where are the expansion work? So the expansion work only occurs here 3 to 4. 3 to 4, which is an isentropic process. So isentropic for the work, you can consider CV. Okay, CV is correct. Okay, but then is it 0.718? So you have to use the formula of Cp equals to gamma R over gamma minus 1, Cv equals to R over gamma minus 1, gamma is equal to Cp over Cv, and R is equal to Cp minus Cv. Those four formulas to find your Cp, Cv, and gamma actually. Okay, so it's not shown here because I have considered it as A. Sorry. Okay, so it's 0.718. Okay, CVT for the work. The expansion work only appears here 3 to 4. 4 to 1 is compressed, 1 to 2 is compressed, 2 to 3 no work. So the only expand only occurs from 3 to 4. Okay, so that is why you got this. So your net work over gross work. So you have work ratio here. That means effective pressure, net work over length of PV diagram. So your length should be V4 minus V2 or V3. Okay, not V1 minus V2. Here again another. Okay, is V4 minus V2 or V3. Okay. There I use V4 here because when I type this or when I paste this, okay, it's V1 minus V2. So it should be V4 minus V2. Okay. 2 is 0.0028. V4 is that. Okay. So that means this is correct. So it can be 4.65 bar. So then the next one is the Carnot. See, remember lowest temperature in the cycle. So the lowest temperature in the cycle should be 0.1. Okay, so the lowest temperature in the cycle, should be 288. Yeah, 288. I think something wrong. I took wrongly something here. Okay, so the lowest temperature. Very sorry very much. Okay, the lowest temperature is here. The highest temperature is this. So you take the lowest divided by the highest temperature. Yeah, something wrong. Okay. Thank you very much.